Okay, welcome to 7.2, Introduction to Logarithmic Functions. Folks, y'all don't have to have a copy of this printed out. You are welcome to just use a piece of notebook paper, do some of the problems along with us, and know that the completed notes will appear in Google Classroom. All right, let's get started. In our warm-up, we talked about exponential functions, and we came up with one to describe what would happen when we double our money. And it looked something like this. We had $1, and we doubled it a certain number of times to get a specific amount of money. Another way we could write this in a more generic form would be to say that y is equal to the amount of money we hope to someday have is equal to our multiplier raised to the power of x, which we can decide depending on what kind of money we're looking at generating. The graph over here, the blue line, represents the money function we played with in the warm-up. This would be y equals 2 to the x power. All right, so that's what we just completed doing. Let's think back to some of our previous learning where we talked about how to find the inverse of functions. The inverse of a function can be found when we switch x and y. So let's take a moment and try doing that, specifically with this equation that we have right here. If we write that with the inverse of that function, then I would say I've got my base. Well, actually, I'm going to switch the x and y, so the y would be here. So there's my y value has switched to becoming an x value. My base does not change. And now my y appears as my exponent. So this function, x equals 2 to the y power, is the inverse of y equals 2 to the x power. That's represented over here in the graph with the red line. The red line is our inverse, which is x equals 2 to the y value. And you'll notice, like we've learned to expect with inverse functions, they reflect across the equation y equals x, and they're mirror images of each other. Their domain and ranges are also reciprocal flips of each other, and that's just what it means to be an inverse function. So it turns out that the process by which we would discover what x could be in order to generate a particular y is important. And so as we talked about in the warm-up, we call that the logarithm. Logarithms are used all over the place, and so they have their own notation. We say that that exponent y is actually the log to base something. In this case, in our case, it was 2, but it could be any number. Log b of x. So this notation can be read by saying y equals log base b of x. And it's just a fancy way of saying that we can find the exponent to which something, the base, must be raised in order to generate a number x. Okay, so that's what a logarithm is in generic terms. Here's the textbook's blurb about what a logarithm is. And it says basically the same thing that we just talked about. Log base b of x equals y value if and only if that base raised to the y power gives you a value of x. An example would be this one. Let's start over here. 3 to what power gives us 27? Well, we happen to know that that's a 3. That can be written as log base 3 of 27 equals y. It's handy because we are very comfortable with this exponential function. It's handy to be able to write exponential functions as logarithms and logarithms as exponentials. That's called converting from one form to the other, and we're going to practice doing that. So here's a conversion. It just tells us how to write an exponential function as a logarithmic function or a logarithmic function as an exponential function. And I've learned from my good friend, Mr. Modesty, that this is called a log roll. And he calls it rolling the log, and it's just a way to remember what the different forms look like. Let's do an example together so you can see what it looks like to take a logarithmic function and write it as an exponential function. So the first thing I notice is that an exponential function, I start with my base, and the base is usually this subscript letter in a logarithm. So I'm going to take my base, 25, and I'm going to write it as the base of my exponent, and I'm going to do a log roll. I'm going to roll my log. Now my exponent becomes this weird fraction, and what it's equal to gets shoved out over here. Why does this work? Let's think about this for a minute. 25 to the 1/2 power equals 5. Why is that true? Well, if you remember from our previous units, the square root function can be written as an exponent that involves a fraction. So the square root of 25 is the same thing as 25 raised to the 1/2 power. And that is indeed 5. So I have written our logarithm as an exponential expression. Let's try again. The first thing I need to do is identify what my base is, because that's going to be the base of my exponential function. Then I'm going to roll my log, and my equivalent becomes my exponent, and the log becomes what I'm equal to. And this should make sense. 3 to the 3rd power is indeed 27. At some point, if you would like to pause the video and try it yourself, it's a great idea. Then you can come back to see if you did it correctly. All right, looking at the next one, we're going to identify our base. We're going to roll our log. In this case, what I'm equal to becomes my exponent. The 1 becomes what I'm equal to. This should make sense because if you remember, anything to the 0 power is just 1. Example 4. Find our base, roll our log. The exponent becomes 1, and what we're equal to becomes the 9. This should also make sense. Anything to the 1st power is just itself. Example 5. Identify your base. Do your log roll. Roll the log. The exponent is what you were equal to, and your log swaps places. 2 to the 6th power is indeed 64. Last one, this one's a little bit more interesting. We're going to identify our base. We're going to roll our log. Our exponent in this case is -2, and that's going to be equal to the fraction 1/16. And you might be asking yourself, why does that work? Why indeed? Let's remember what happens when you have negative exponents. 4 to the -2 can be rewritten as a fraction, 1/4 squared. Remember, when you're negative, if you flip, you become positive. And we know that 4 squared is really just 16. So that seems to work. All right, that's taking a logarithmic function and rewriting it as an exponential. Let's see if we can do it the other way. And of course we can. What a setup. I've kept this up here because it helps me to remember what the conversion is. In this case, we're going to write these as logarithmic functions. We're not going to evaluate them. We're just going to write them as logarithmic functions. And we always do that by starting with the word log. I need to identify what my subscript is going to be, what the base is, log base 3, and then I'm going to roll my log. My exponent becomes the equal to, and this becomes the number for my log. So I've got log base 3 of 243 equals 5. That's all there is to it. Let's try again. I start with the word log, identify what my base is going to be. That's my subscript. And then I roll my log. What I was equal to becomes what I'm taking the log of, and my exponent becomes what my function wants to be equal to. Another one. Log, identify your base. Log base 2, that's my subscript. Roll my log. What I'm equal to becomes my log, and my exponent becomes what I'm equal to. I can keep going. We could do this all day. Log, identify your base, that's your subscript. Roll your log. Your equal becomes the log value, and your exponent becomes what you're equal to. Example 3. Don't panic because a fraction here. We do the same steps. Log, identify your base. If you feel more comfortable putting log of 0.5, you could do that as well, because this is a friendly fraction. Next thing I'm going to do is I'm going to roll my log. What I'm equal to becomes my log. My exponent becomes what I'm equal to. Last one. And I'm going to argue there's a typo here because 10 to the first power is actually 10. So I'm going to throw that in there. And then I'm going to write this as a logarithmic function. Log, identify your base. That's your subscript. Roll your log. So what I'm equal to becomes my log, and my equal to becomes my exponent. There we go. Very manageable. Keep practicing. You can make up your own problems for this. This alone, however, is not going to be quite enough for us to continue working with logs. The next thing we need to do is figure out how to evaluate them. So if I give you a log, could you figure out what an x value would be to give you a particular log value? So let's talk about what those steps are. First thing I need to do is I need to create a variable. In example 1, I've done that for you. In example 2, you'll notice there's no variable, so we'll have to create one. The second thing we do is write these in exponential form, and then we can evaluate either using a calculator or by doing it by hand. We can evaluate and find the value of x. So let's do that. Let's rewrite this as an exponential function since I've already created my variable. 8 is my base. I roll my log. And when I do that, the x becomes my exponent. And I'm looking for the value of x that 8 can be raised to give me 512. So from here, I can either use a calculator or I can do this by hand to figure out what the value of x is. If I'm using a calculator, I would put into the y equals function 8 raised to the x power. Then if you look at your table, you should be able to see all the values of x in the left-hand column, and the values of y will represent 8 to the first power, 8 to the second power, and 8 to the third power. And you can scroll down that right-hand column until you find the number 512. The x associated with that would be the answer or the evaluation of this function. We can also do this by hand. I can start with 1. and multiply by 8. It's very similar to, it's exactly the same as what we did in the warm-up. 1 times 8 is 8. Times 8 again is 64. Times 8 again. There's my 512. So to find the value of x, I just need to count how many times did I need to multiply 8 to get 512. 1, 2, and 3. So x equals 3. 8 to the third power gives me 512. Let's try another one. I'm going to first create my variable. I'm going to write this as an exponential function. Sorry, slippery little fella. 5. Going to roll my log so that x becomes my variable. That's what we're looking for. And I'm trying to find 5 raised to what value will give me 125. Again, your calculator's your friend, but if you want to do it by hand, you can. 1 times 5 is 5, times 5 is 25, and times 5 again is 125. Count them up, 1, 2, 3, and again, coincidence, x equals 3. 5 to the third power is 125. Another, we create our variable. We write this in exponential form. 4, roll my log. 4 raised to some power is going to be equal to 256. Use the calculator with y equals 4 to the x, and then find the table function, or do it by hand. 1 times 4 is 4, times 4 is 16, times 4 is 64, and finally, times 4 one more time gives me 256. So if I count them up, 1, 2, 3, 4, it took 4 iterations to end up with 256. So when x equals 4, 4 to the fourth power will be 256. One more. 3 more, actually. 4, 5, and 6 examples are a little bit more interesting. They are slightly more complex, but nothing that we can't handle. First thing I do, for example 4, is create a variable. Then I'm going to write it as an exponential function using a base of 64. I'm going to roll my log. Now my exponent becomes the x, and I'm looking for a value that I can raise 64 to that gives me 8. So you might be thinking, what the heck? Ms. Palmer is going to jump ahead and tell you that this value is going to be x to the 1/2. And if you're scratching your head, here's why. If you will remember, when we talked about rational expressions, we learned that the square root of 64, or the square root of any number, can be written as that number raised to the 1/2 power, because 2 is the index of that root that math people are just a little too lazy to write. So 64 to the 1/2 is the same thing as the square root of 64, and in this case will give us 8. Example 5, log base 5 of 1/5 equals x. We have to create that variable first. Then we need to write it as an exponential function. I'm going to identify my base is 5. I'm going to roll my log. So I'm looking for the value of 5, the value that 5 can be raised to, such that it gives me a fraction of 1/5. And if you look at example 6 on the previous page, that might give you a hint. What we talked about is that when we have negative exponents, it flips my base. So in this case, I am looking for a value of x that makes 5 become 1/5. And I'm going to tell you that it's x equals -1. Why is that true? Well, if you remember, when you have a negative exponent, so 5 to the negative 1, we flip, and that become 1 over 5 to the first power, which is just really 1/5. All right, one more. This one is particularly interesting. It involves lots of fractions. Fractions are friends, remember? First thing I do is write it as, create my variable, and then I'm going to write this as an exponential function. 1/6 is my base. I'm going to protect him. And then I'm going to roll my log. My exponent becomes an x, and I'm looking for the value that I can raise 1/6 to evaluate to a 1 over 216. We could use our calculator for this, but that's going to be a little complicated because 1/6 is not a friendly fraction. It's a non-terminating decimal, but we can do it by hand fairly simply. If I start with a 1 and multiply by 1/6, I get 1/6. Remember, when dealing with fractions, we multiply numerator times numerator and denominator times denominator. I need another one. 1 times 1 is 1. 6 times 6, 36. Still not there, so I'm going to multiply by 1/6 again. 1 times 1 is 1. 36 times 6, 216. So I just need to count them up. 1, 2, 3. It took 3 iterations, x equals 3, sorry, x equals 3. Cross that out. I have to raise 1/6 to the third power in order to get 1 over 216. And there we have it. We've evaluated 6 different logarithmic functions, discovering what that exponent would be to give us a particular value.